angular part. Not surprisingly, the angular part is the spherical harmonics we studied in week 4, which are the eigenstates of angular momentum. You can verify this, but just believe me, this is true. And the radial part, when I say the angular part is the spherical harmonics, I mean the angular part is the spherical harmonics independent of what kind of central potential we are considering. For all of these 3 maybe and more examples of the central potentials, this part, the angular part, is always the same. What's different is the radial part. The radial part, by just using the separation of variable method, you will see the radial part satisfies this kind of equation. It's kind of complicated. And if you define something called U in this way, U has this equation, which in principle you can solve, again, using the mathematical methods in physics. So to summarize, the lesson here is that is really the angular part of the eigenwave functions for all the central forces are the same. They are just the spherical harmonics. But the radial parts are determined by the specific central potential. And we really have to solve this equation in order to understand this part of the wave function and also the eigenstates and eigenenergy. Any question here? I assume you have learned separation of variables in the previous class, so I will not repeat it here. Okay, so this is the general properties of the central potential problem. Now let's look at a very important example. That is the example of a hydrogen atom, which is the simplest atom, the first atom in the periodic table of chemical elements. It has only a proton and an electron. The proton is very heavy compared to the electron, so we can assume the proton is just sitting there without doing anything, and the electron is moving under this Coulomb potential. Okay, let me ask you some question. What approximation am I making here? How is it? So based on what you understand from the electromagnetism, when I say the electron is moving in this Coulomb potential, is this an exact statement or approximate statement?
You say that the proton doesn't move?
Yeah, I say that the proton doesn't move, that's one approximation. This is because the proton is much heavier than the electron. Is there another or more assumption or approximation besides this?
The electron is not radiating.
The electron is not radiating? That's indeed another assumption. So in principle, in electromagnetism, we know that if we have some charged particle that is not moving with a constant velocity, then it will radiate some electromagnetic waves, right? But that seems to be completely ignored here.
There's no spin-orbit interactions.
There's no spin-orbit interactions. Very good. So far, we have not discussed the spin-orbit interactions. Later, we will discuss it. Spin-orbit interactions are some effect coming from relativity. Yeah, that's another assumption. And what other assumption? Of course, speaking of relativity, we know another assumption is that this kinetic term is non-relativistic, right? In principle, is the Einstein thing, something like p squared plus mc squared something, right? But yeah, that's because the speed is still quite low. Let's assume this non-relativistic assumption. Is there another assumption? Yeah.
The electron has a definite position.
I'm not assuming that.
No?
I'm not assuming that the electron has a definite position. You see here, this R is a quantum mechanical operator. The electron has a wave function. But good point. Let me give you a hint of the other assumption I'm making here. This assumption is not regarding the electron itself in some sense. It's regarding the electromagnetic field. Yeah.
Aren't you assuming the proton has a definite position?
I'm assuming the proton has a definite position, that's true. I'm really waiting for you to say another assumption, which is regarding the nature of the electromagnetic field. Can you recall? Let me tell you. In electromagnetic, when you took electromagnetism, you know that the electromagnetic waves they propagate with the speed of light, right? This Coulomb potential is assuming the speed of light is infinitely large. There's really some small delay effect that corrects this Coulomb potential. This radius sometimes needs to be replaced by the radius minus the speed of light times some time, something like that. If you take into account that the electromagnetic field itself is a dynamical object, it also has time dependence. This is of course related to that the electrons will radiate. But now in the regime where the electrons they don't move that fast, and we will just assume that the speed of light is infinitely large, and we have this instantaneous interaction. Yeah.
But if the proton doesn't move, isn't it just a steady case even with finite light speed?
Even if the proton doesn't move, there will be interactions and there will be feedback between the electron, the proton, and the electromagnetic field. It's not this simple. In fact, actually today, today in Singapore time, the Nobel Prize of this year will be announced in physics. In fact, the Nobel Prize for 1965 was awarded to Feynman, Schwinger, and Tomonaga, I think. That's how his name spells. The contribution they made to win the Nobel Prize was to understand this kind of effect, even if the proton is fixed. They developed the whole thing called relativistic quantum electrodynamics. The key step to develop such a theory is the thing called renormalization. Based on that, they were able to extract many things. Okay, so here, for simplicity, let's just take the speed of light to be infinitely large. The electromagnetic field is something static instead of dynamical. So the equation that governs the motion of the electron is just the equation here. It's just what we naively imagine. Then our task, according to what we just said, our task is to solve the eigenwave function for the radial wave function. And the method of solving this equation is one standard method is to expand this wave equation, the radial part of the wave equation in terms of Taylor series. And then our goal is to understand the coefficients of the series. You can derive some recursion relations of the series, and you demand the convergence, that the wave function can be normalized. Then you will see, you will find out these coefficients. You can look at these sections in these books to see how it's really done. And that's not very important here, and I assume you have learned this in mathematical methods in physics too. So after all the process, you can solve this wave equation, which is this horrible mess. It's very complicated, right? To be honest, when I took quantum mechanics class, I never solved this. I also didn't learn the hydrogen atom solution. I learned this wave equation only when I prepared this lecture for you. But let's comment on the important features of this horrible mess. You see, in this wave equation is parameterized by three. Of course, it's parameterized by three coordinates: the radius r and the two angles theta and phi. But more importantly, it's also parameterized by these three numbers called n, l, m. They have three names. N is called a principal quantum number. L is called the angular quantum number or orbital quantum number. M is called the magnetic quantum number. So L and M are precisely the same L and M that appear in the spherical harmonics, which tells us the eigenvalues of this state on the L squared and LC. What about this n? This n is some other number that appears in the wave function. And it appears in a very strange way. It's very complicated, as you can see. And also there's another parameter, which is this a. This a has a name called Boyle radius. It roughly characterizes the average distance for the ground state of the electron and the proton. In the ground state, the average distance between the electron and the proton is this a. It's useful for you to remember at least have some rough idea of how large this a is. It's of the order of smaller than nanometers. It's very small. And based on this data, you can also kind of imagine if we consider some macroscopic object like this one, is made of some crystals, right? Like the silicon chips, they are made of some crystals, and you can imagine the distance between those atoms in those in the big system, like in a huge crystal, the distance between two atoms are also of the order of 10 to the negative 10 meter, which is 0.1 nanometer. That's the length scale of atoms in a big system, in a crystal. Okay, this is the wave function. It's something very complicated. I don't encourage you to remember it. You can refer it. You can refer to some books to find it. I also don't remember it. I think what's more interesting is the energy spectrum. The energy spectrum takes this form. So from our previous discussion of this degeneracy, we know there will be this kind of degeneracy. So in principle, this energy eigenvalue should depend on two parameters. One is some parameter coming out from solving the radial part of the wave equation, and this is precisely this parameter n. The other, in principle, it can also depend on the angular momentum magnitude, which is L. But really, after solving the wave equation, what we found, this was originally solved by Schrödinger, what he found was that this energy eigenvalue only depends on n, the principal quantum number. It doesn't depend on L or M. And in particular, it depends on n in this particular way is equal to the ground state energy divided by the square of the principal quantum number. And the degeneracy is n squared. There's a degeneracy which is n squared. And the n and L has this relation. For a fixed n, L cannot be arbitrary. Instead, it can only take values from 0 to n minus 1. And this is also why the periodic table of chemical elements are arranged in that particular way. Because basically, as we go down and down in the periodic table, the n can be larger and larger, so L can, in principle, be larger and larger. The number of states there can be more and more number of states. The magnitude of this E1 is of the order of electrovolt. Do you know how large is 1 electrovolt? In terms of Kelvin, how large is it? Yeah. How large? Kelvin. You know what Kelvin is, right? It's the measure of, it's the unit of temperature. So in terms of how large is 1 electrovolt in terms of Kelvin? It's about 10 to the 4th Kelvin. So it's 10,000. It's about 10,000 Kelvin.
Kelvin are not the energy unit, no?
Sorry?
Kelvin are energy unit?
Kelvin times kb is an energy unit. By Kelvin, I mean not only me. When you heard people say the energy scale being how many Kelvin, they mean how many Kelvin times kb. Kb is the Boltzmann constant. So 1 electrovolt is about 10,000 Kelvin. Another thing that's good to have in mind is, you know the Fermi energy of a system. If we have many fermions, as we learned from Pauli's exclusion principle, they will just occupy, if they don't interact, they will just occupy the single particle energy levels. And here you see this is a piece of key. Many of you, I think most of you also have some pieces of keys. They are made of metals. We can ask how large is their Fermi energy in the unit of Kelvin or in the unit of electron volt. Do you know how large?
200.
This is a question, if you go to a PhD in physics, this is a question that you can encounter in a qualified exam. I went to a qualified exam last week and I did ask this question to a student from, I cannot say more. But do you know how large is it roughly for this key? It's also about 1 electron-volt, which is 10,000 Kelvin. But our room temperature, you see our temperature in this room, is just about 300 Kelvin, which is much, much smaller than the Fermi temperature of these metals. These are just ordinary metals that we see every day. So that's why in the first class I said quantum mechanics is really not far away from us. Because even under our normal condition with this kind of temperature, from the perspective of those ordinary metals, their Fermi temperature or Fermi energy is that large. Our room temperature is really, really small for them. So from our perspectives, maybe Singapore is a very hot place. But from the perspectives of the metals, Singapore is in the low temperature regime, and the quantum effects are important. Okay, those are about the numbers. But the really peculiar feature is this degeneracy. I want to ask you first that I think I said this multiple times, but let me just ask you again. Why should we expect that this energy should not depend on the M magnetic quantum number? Why should we expect that?
The Hamiltonian JZ. Sorry, J.
Because the Hamiltonian commutes with Jz? The Hamiltonian commutes with Jz just means Jz and the Hamiltonian have simultaneous eigenstates. This doesn't mean all those simultaneous eigenstates should have the same energy level. Because Hamiltonian commutes with what? It is because Hamiltonian commutes with something, but what? Yeah, it's because the Hamiltonian commutes with J plus and J minus. J plus and J minus, they will relate states with different Jz eigenvalues. And because J plus and J minus, they commute with the Hamiltonian, those states are related by them, those states will have the same energy. That's why this energy will not depend on M. For different M's, they will just have the same energy. But in principle, it can depend on both N and L. But it only depends on N. That's something very strange. By the way, why it doesn't depend on M is also a question you may encounter in the qualified exam. Even why it doesn't depend on L is also a question that you may encounter, but usually you are not required to answer that question. However, in problem 1 of assignment 8, you will understand why it doesn't depend on L. Historically, it's actually quite funny. Schrödinger solved this Schrödinger equation and found those solutions, and also these energy eigenvalues, and also the degeneracy by solving the Schrödinger equation. However, historically, this spectrum was not first obtained by Schrödinger. It was first obtained by Pauli without using the Schrödinger equation, even without knowing the Schrödinger equation. And in assignment 8, you will see how Pauli did it. You will not do the whole calculation that Pauli did, which was quite complicated. You will only do the simple part. Okay. Let's make sense. Let's check that the degeneracy really makes sense. So here I said for a fixed value of n, L can take values in this range. And we know for fixed L there will be this degeneracy. Let's make sure that the n squared for degeneracy mentioned here is indeed equal to the total degeneracy of all these different L's. Check this. I think maybe this is too simple for you. We will just need to sum these things up, right? This summation is easy to carry out. It's the summation that Gauss was able to do when he was maybe 7 or something. He was able to calculate 1 plus 2 plus 3 until 100. Using the same method, you are able to calculate this summation and you find it's n squared. Okay, so this part is understood. This degeneracy makes sense, but at this point, we have not explained why those states with different L eigenvalues should have the same energy. You will understand it in this part. One more thing I want to comment is, as you know, the electron has spin 1/2. For electron, the spin can take two different values. So for each energy level, there's actually also the additional 2 for degeneracy due to the spin. So the total degeneracy, if you take into account the spin, is 2n squared. Okay, any questions about the properties of the hydrogen atom? So in summary, the thing we need to know about the hydrogen atom, first, I think one of the most important things to know is the typical size of an atom is of the order of 0.1 nanometer. That's something which is good to know. The other thing is the typical energy of the electrons bound to some atom is of the order of electron volt, which is 10,000 Kelvin. That's quite large. Do you know how large is it in terms of frequency? Why is frequency the unit of energy? That frequency times the Planck constant is. How large is this frequency? In terms of frequency, this energy scale is in the range that can be seen by us. You know, our human beings can only see a particular range of spectrum of electromagnetic waves, and this energy scale is in that range. And this is also the principle. This is the principle behind which we can observe such frequency using this kind of spectrometer. Maybe you have done experiments using the spectrometer. There are some small telescopes, and on one side there will be some atoms, either hydrogen, usually sodium, and then there's this prism, and by rotating one of these telescopes, lights with different frequencies will have different index of refraction rate. So when light goes through the prism, it will be propagating in different directions. Then by moving one of those telescopes, you will identify the position or the angle of the light, and then you can read off the frequency. And you can, many 100 years ago, people observed experimentally this pattern of the frequency. And this was really how quantum mechanics started. People tried to understand this kind of frequency. And the frequency one observes is just the energy difference between two energy levels. According to the expressions of En, we get this kind of expression. In case you haven't done this experiment and you will do it in the future, I want to tell you this is the experiment I hate the most when I was an undergraduate student. It took so much time to calibrate this device. I remember at that time we had lab classes on every 2 Thursdays, and if I had to do this experiment, I had to stay there from 1 p.m. until 8 p.m. without really being able to calibrate the device, and then I had to go there during the weekend to do it again. It was really painful. Okay, any questions about the hydrogen atom? Okay, if not, let's take a break until 50. And then we will talk about something fancy, something which you usually don't see in other classes.
So can I ask, like, you mentioned like the energy scale of, like in terms of the temperature is 10,000 Kelvin, but like what is the physical meaning of it? Because like obviously it's not the thermodynamic temperature in the sense of like interacting with the environment, but I don't know what the meaning of this 10,000 Kelvin is.
What's the meaning of what?
Like you mentioned the energy scale of the hydrogen atom, that is at 10,000 Kelvin.
Yeah.
Sorry, and the Fermi energy of the metal as well.
Yeah.
I don't understand what's the physical significance of this quantity.
Oh, I'm sure you have taken thermodynamics and statistical mechanics. No? Okay, that's why you don't know. It's okay. Now after knowing this, you know it. So usually you see for this kind of big systems, we think maybe quantum mechanics is not important. We usually think that quantum mechanics is important for some small physical systems like a single atom, single molecule, and so on. But actually for big systems made of many, many atoms, molecules, and so on, maybe quantum effect is also important. In particular, it is important when the size of the wave function, the wave function has some size, right? And in thermal equilibrium, the states also have some typical de Broglie wavelength. So in thermal equilibrium, with a fixed temperature, there will be some characteristic momentum of the system, because temperature essentially, in some sense, captures how fast the atoms move. There's some characteristic momentum. And according to the de Broglie, this can be translated into the wavelength. That's some length scale. So if we compare these two length scales, one is the length scale of the quantum wave functions, the other is the thermal length scale, and also there's the distance between them. If this thermal length scale already combines thermal physics and quantum physics, if this thermal scale length scale is even bigger than the average distance between two atoms, then quantum effect will be important, because they don't really look like particles anymore. They look like waves that can overlap, even at some finite temperature. And to compare the average distance with this thermal wavelength is essentially, for fermionic system, is essentially to compare the temperature of the system and the Fermi temperature. Now the Fermi temperature is about 10,000 Kelvin, but in Singapore we are still the weather is too cool, only 300 Kelvin, quite low compared to the Fermi temperature. So all those metals behave quantum mechanically as macroscopic objects.
Maybe next time on TA or 2135 and learn about.
Thank you.
Yeah, it's not real. Yeah. Sounds also a bit funny. You see, it's a forward seat, so reverse seat. Oh, but look at the yellow is positive, purple is negative. I think the code took this as positive, this as negative, not forward seat, reverse seat. But yeah, I mean, the good thing is this is real. It's quite funny. Oh, did Kodeshi give you that, or did you do it? Oh, so the previous measurement we did, he wrote two code files, one to split the data, another one to process the data. But for our recent measurement, I had to rework quite a bit of the code, because one, the data is in a different format, another one because the way we ran the field is different this time around. So last time it's like a minus something, plus something. But now it's from 0 to plus, and back to 0, back to minus, back to 0. And yeah, so there was some indexing issues.
Okay, I guess we can get started. Jianxian's question was good. It's a question about motivation. If you have questions, not just about the content, but about the motivation, please just ask. It's okay. It's good. Those are good questions. Okay, now, so after 5 minutes, do you have more questions about this part? just a fact. It's derived from relativistic, either quantum mechanics or quantum field theory. Maybe let me say more about this. One of you mentioned there can be spin of the coupling, meaning the electron has a spin and the electron has the orbital part. In principle, the Hamiltonian can have a term that's proportional to S dot L, where S is the spin angular momentum and L is the orbital angular momentum. In principle, this can happen, right? In the Hamiltonian we were considering, we didn't have this term because the coefficient in front of that term is quite small. That term can be derived using relativistic quantum mechanics or relativistic quantum field theory. That's why I said it's coming from relativity. But you also see this is another thing that I wish I have known earlier, but I didn't know until after some years when I started doing my PhD. The thing is, from this Hamiltonian, you naturally think, from this kind of Hamiltonian, you will naturally think the spin angular momentum commutes with the Hamiltonian. The spin angular momentum is something that should be conserved. However, relativity tells us spin angular momentum should really not be conserved. By default, it should never be conserved. The spin angular momentum itself. Instead, only the spin part of the angular momentum and the orbital part of the angular momentum, their sum is conserved. In a more fancy language, it's saying that the relativity only has the Lorentz symmetry. It doesn't have SU2 cross SO3 symmetry. The last sentence can just be planted in your minds, and it will some trees will grow up later. Okay, if you don't have further questions, let's continue to this part, quantum electrodynamics. By quantum electrodynamics, I just mean how a quantum particle moves in an electromagnetic field. And I will, at the beginning, I will consider the electromagnetic field to be quantum, and later we will take this semi-classical limit, assuming it's classical. Okay, to talk about this part, let's start from classical electrodynamics, which you have learned in your electromagnetism class. So to consider how a classical particle moves in a classical electromagnetic field, we just need to use the laws by Newton, Maxwell, and Lorentz. Newton's law says the force is related to the acceleration by the mass. The Maxwell equation says this, the Maxwell equations say how the electromagnetic field are related to the properties of the particles. So E is the electric field, B is the magnetic field, and this rho is the electric charge density, epsilon 0 is the dielectric constant, mu 0 is something whose name I can never remember, permeability, I think. Yeah, those are the Maxwell equations. And those electric and magnetic fields are related to the forces that the particle experiences via this equation. So there's this electric force, and then there's the magnetic Lorentz force. And this is the Lorentz force law. So combining these three equations together, you see that if we know the background electromagnetic field, then in principle, we can just plug in this equation into the Newton's second law, and in principle, we can solve the motion of the particle. That's the classical story. Now you see in the Maxwell equation, I'm using the red color to differentiate this equation from the other equations. By the way, maybe it's good to ask this. What's the name of this equation?
Gauss law.
It's called Gauss law, right? Because I said it here. I hope you also know it. So the Gauss law tells you if you want to understand the total charge inside some volume, you can just integrate the electric flux over a surface that encloses this volume, right? This is something you often use. What's the name of this equation? I guess it doesn't have an equation except it's called magnetic Gauss law. It's kind of like this. It's kind of like this one, except the right-hand side is equal to 0. It essentially says within these equations, there's no particle that can emit magnetic flux. But the magnetic monopole will be such a particle. So this equation in principle should be corrected if magnetic monopoles exist, which have not been confirmed so far. What's the name of this equation? This is Faraday's law, right? It tells us why we can have electricity by turning some circuit around some magnetic field. Does this equation have a name? Good. I actually didn't remember this name. Yeah, those are the 4 equations. People often say, sometimes you see, this is a question I got before. People often see as physics evolves, we have seen more and more beautiful equations. You see, the Newton's second law consists of only a single equation, which looks pretty simple and beautiful, right? But look at this horrible mess. It consists of 4 different equations. Why do people think these 4 equations are also, in some sense, more beautiful than the Newton's second law? Do you know why? Sorry? I can predict light? Yeah, that's beautiful, of course. But suppose I wasn't able to do that. Just by looking at these equations, can I sense the aesthetic beauty of these equations? It's not that easy, right? No?
There is certain symmetry between B and E.
What kind of symmetry?
Like the equation for E and E are very similar.
Yeah, very good. So suppose we just consider the electromagnetic field in vacuum without any particles. So rho is 0, J is 0. And then you will see the equations for E and the equations for B are very similar, right? If we change E to minus B, if we change E to B and B to minus E, then the equations still hold. You see, I was very careful in saying E to B, B to minus E. This has a name called the electromagnetic duality or S-duality. It turns out to be something very profound, and is related to also related to one of the most profound mathematical programs at this point of time, called the Nernst program. This is a program that's supposed to connect all areas of mathematics, and this S-duality also combined with something called T-duality, they are related to that. And that's actually a subject that I don't really know well. There's another reason. Do you know how Einstein proposed the theory of relativity? Einstein did it by looking at these equations. Relativity is hidden in these equations. Maybe in this form it's not obvious at all, but you can actually write these 4 equations. You're just using a single equation that in which the relativity is more manifest. Okay, so much for that. So I'm using the red color for this part because you may think these 4 equations are equally important. However, this Gauss law actually, in some sense, is more important. Let me write the Gauss law in a different form. So let me decompose the charge density into 2 parts. So this charge density is decomposed into some background charge and some change on top of it. Yeah.
What happens when Gabriel?
It's a typo. Thank you. Yeah, let me decompose it in this form. At this point of time, you may also not appreciate this freedom. So the point here is I have the freedom to separate out some background charge. Later, when you encounter something called quantum spin liquid or something, you will see this freedom is very useful. Okay, and the point here is that Gauss law is somehow more important. Yeah.
The background charge, what is it? Minus.
Just I like it. It will be more convenient. You can define it to be plus. That's your freedom. if you like, you can define it to be plus. But the point is, one can separate out some background charge. Okay. Also in electromagnetism, you learn something called vector potentials and scalar potential. You know that the electromagnetic fields can be encoded in this V and A, such that electric field is given by V and A in this form, and the magnetic field is given by this expression, right? And I think when you learned electromagnetism, you hate the V and A. When I learned it, I kind of hated V and A because it seems V and B, they are something more physical, something that we can really measure. But the V and A, they are not something that's physical. Instead, there's some redundancy in V and A. V and A and this kind of V and A, this kind of transformed V and A, they lead to the same E and B. This transformation, which takes a function f and changes V into this one and A into this one, this transformation has a name called gauge transformation. I think gauge transformation, the gauge is just a name. Let's not worry too much about it, but there's this gauge transformation or gauge redundancy. There's another thing I want to mention, which is typically not covered in the electromagnetism class. That is, we have learned, I think you have learned classical mechanics, right? You know, for a dynamical system, there can be the coordinates or generalized coordinates and their canonical momentum. They have specific Boson bracket. It turns out minus epsilon 0 E is the canonical momentum of A. It's not at all obvious, but you can derive it, for example, by looking at the Lagrangian of the Maxwell equation. There's a Lagrangian of the Maxwell equation using which you can derive the Maxwell equations. The Euler Lagrange equation of that Lagrangian is the Maxwell equation, and from there you can just using the standard definition, you can figure out what is the canonical momentum of what, and you will see the canonical momentum of A is this quantity. What that means is the Boson bracket of this and this is this. You see, in classical mechanics, we say X and P, Xi and P, X and P are canonical conjugate. P is the canonical momentum of X. So the Boson bracket of Xi and Pj is delta Ij, right? Here is the generalization of that. And also the canonical momentum of V is just 0. Let's just take this for granted. Let's not derive it. It's just something that's true, some fact. Okay. Then it turns out those seemingly unnecessary vector potentials, which has some redundancy, they are actually essential in quantum physics. Because in quantum physics, so far, we always use Hamiltonians, and also, although we don't talk about it, we can also use Lagrangians to describe the system. We don't just use forces to describe the system, right? If we just consider a classical particle in the classical electromagnetic field, the Hamiltonian is this one. This is something I think you have learned in electromagnetism. And then based on what we discussed in week 3, we know the Hamiltonian, the quantum Hamiltonian in terms of the creation and the annihilation operator takes this form, right? It essentially means we have A dagger A here. It essentially means if we have more particles, we have more such Hamiltonians. Okay, this is the quantum Hamiltonian. And the more important thing is really not about the Hamiltonian, but the structure of the Hilbert space, or is about the what is about the basis states. What are the basis states that of the Hilbert space which this Hamiltonian acts on? The most naive basis state is what we learned before in week 2. They are the basis state of fork. We have a vacuum state, and we have one particle state, we have two particle states, and so on and so forth, right? That's the most naive guess. The important thing is this is not the basis state here. To appreciate that, we first notice this Hamiltonian is invariant under a huge set of gauge transformations. You can check in this Hamiltonian, if I take any function f, which is a function of r, if I change this annihilation operator into this annihilation operator, it's the original one multiplied by a phase factor. And if I change the vector potential into this gauge transformed one, you will see this Hamiltonian doesn't change. Let's check this. So under this transformation, all we have to check is under this transformation, this thing becomes so the phase factor can be moved through the derivative. This is not very trivial because you see this. If I just do this transformation, what appears is first this A will be changed into A plus this gradient of f, and at the same time this little a will have this phase factor. Importantly, this derivative here acts on both the phase factor and also a. So when it acts on this part, it will pick up a term that will precisely cancel this one, right? If I act this derivative here, it will pick up this term, precisely cancels this one. So it's like these two effects will cancel. That's why we get this. So when I act the derivative on this product, I can first act it here without touching anything here, or I can first act it here without touching anything here. If we first act it here, it will pick up a term that's precisely q times the gradient of f, which precisely cancels this one. So this is saying this derivative is as if it doesn't act on the first part, it only acts on the second part. That's why it's equal to this one. Then you see this derivative can be moved further forward, and coming from this A dagger, there will also be the derivative. Under the gauge transformation, A dagger becomes this one. These two phase factors just cancel each other. That's why the Hamiltonian is invariant. But except this is a huge set of gauge transformation because f is a function of r. I can take any function of r to do the gauge transformation. This is kind of different from the previous symmetry transformation we considered. For the symmetry transformation, we just have a single parameter to parameterize the symmetry transformation. For example, previously when we talk about translation, it's something like this. We just have this single parameter to parameterize the translation, right? When we talk about rotation, we basically just have a few parameters. Like here, this n tells us around which axis I want to do the rotation, and this theta is the angle around which I want to do the transformation. Importantly, these are just a few parameters. Here, this f of r is a generic function of r that have nice properties like this. For example, it's smooth and so on. This is a huge set of there's a huge parameter set for such functions. Yes.
So in this case, is the exponential e to the power of I q over h bar f r more than a phase?
More than a phase?
It's more than a phase.
It is a phase, but it contains many parameters.
Because when you take the gradient of say gradient operator of that, it is different from the gradient of f will come out.
Yeah.
So it seems to be more than a phase that all we used to see.
It is just a phase. Are you asking what is an operator?
let's say you have a particle that's the creation of this as the hot space, maybe. Then you have a particle state.
Oh, a good question. You are basically asking, previously I said this is not the red basis. Is the red basis some phase time space? Is this your question?
Sure, and then there's another question.
Yeah. The answer is no. I will tell you the basis later. But yeah, this thing is just a phase. It's just like e to the I 2 pi over 3, something like that. Okay. Previously we said, yeah. We want to identify under what kind of transformation the Hamiltonian is invariant. It turns out to be invariant under this kind of transformation. So previously we said momentum generates translation, angular momentum generates rotation, and so on. Now we can ask what kind of thing generates this transformation, and it is the Gauss law that generates this transformation. What this means is, suppose I read the Gauss law in this way. G stands for Gauss. If this is equal to 0, that's the Gauss law. I realized I'm using inconsistent notations. This background charge here, this is the excess charge. This is the background charge. I'm using this sign here. Yeah, previously there was a typo. This whole thing is the total charge. This is the background charge. This is the excess charge. And if this is equal to 0, that's the Gauss law. When I say the generator of the gauge transformation is this, what I mean is if I act this kind of unitary operation on this operator A, I get this dz transformed version. In this capital A, I get this dz transformed version. You see, the expression of this thing is kind of complicated. In the exponential, I have not only this this Gauss law, but it's multiplied by this arbitrary function and integrated over the space. By using these two equations, you can verify that this is true. Is the statement clear now? Not the reason, but just the statement. The meaning of these equations. If you plug this equation into here by using these two equations, you get the two middle equations. That's the statement. Okay, it seems the meaning of these two equations are clear, but I have not explained why, and now prove it. Plug this into these two equations and use this, you will see that this is true. Just do it by brute force. The first equation should be kind of familiar that you did it many times. So what appears here is something like a dagger a. E to the I dagger a times theta conjugate with the a, then a will just pick up a phase.
Does the f diminish at infinity?
Yeah, let's assume that, or let's, for simplicity, consider putting the system on a system without boundary. Say we will impose periodic boundary condition for a finite system, or put the system on a sphere, or other closed manifold. Or space-time doesn't have to be flat. Yeah, maybe it may be more useful if I do it for you. Yeah, let's look at the first one. For notational simplicity, I will write this thing as U. I will write this thing as U. So I want to calculate. What I want to calculate is U dagger. And you see, inside U, inside this G, there's E, there's A dagger A, and there's rho. This rho is just a C number. It commutes with everything, so let's not worry about it because the rho 0 in the U part and in the U dagger part will cancel. And this E part, E commutes with this little a, so this E part can pass through and also cancel the E part from the U dagger, but the A dagger A part will not just pass through. Right. Then we need to proceed. Oh, I missed the F. Then we need to proceed with this. What equation should we use? It's always the e to the I times b times e to the minus I thing, right?
In your lecture, you use plus and minus for the unitary. That is U dagger U. Is that U dagger? It is in that, it's not in that.
It doesn't matter.
I mean, yeah.
I'm just trying to check that these two equations are true. If you prefer, you can call this thing U dagger. I'm calling it U. You can call it U dagger.
Yeah, like,
And then there's some nested commutator, right? Let me just carry out the calculation for the first term. You can do it for the rest of it. The commutator between this part and this part, according to here, is just minus. That minus will convert this minus into plus. Is minus a with the derivative with the delta function, and you will see this becomes the dot term represents the terms coming from the nested commutators. If you carry out everything, you will see this will just be equal to e to the I q h bar times f times a. You can kind of expect this because you have done many times that this is equal to this. And what we are talking about now is the generalization of that. They come from the same reason. It's the same derivation. Now let me look at the second one. The second one is maybe more complicated or more subtle. we want to evaluate this one, right? This one is actually also not that hard because we just apply the same equation before. We will have just this. We will have this and then nested commutators, right? But notice the commutator between E and A is a C number. It's not a quantum operator anymore. So if I take the nested commutator, all the nested commutators are just 0. There's no nested commutator. They are just 0, right? Because this commutator is just a C number. Then if I keep taking the commutators are just 0. This is a number, it's not a quantum operator anymore. Okay. Now let me do an integration by parts, and then it's important that the f or either this integration has no boundary or near the boundary f goes to 0. The expressions appearing here would be this one. Finally, I just have to use this commutator here. This commutator. I think there's an H bar here. I missed the H bar here. The last step just comes from this commutator. Any questions?
I have a random question. So, I understand why maybe in Poisson bracket the vector potential at the E is not 0, but for in the pass through quantum case, A is technically a function of R position. So, say if you pass it to quantum, A is a function of the position operator, and E is also a function of the position operator. And now you're saying that they don't commute. Why?
So the question is, from the boson bracket, how can I obtain this quantum commutator?
No, but as in for Poisson bracket, you just assume that in the quantum case, the operator follow the same IH bar.
Yeah, replace one by H bar.
Yeah,
That's the rule of quantization.
Operators.
Mhm.
But the A, like the A is a function of position operator, and the E is also a function of position operator.
No. Okay. This is something that's an important point. A is not a function of the momentum of the position operator. E is not a function of the position operator. Here in this language, these two positions are not operators anymore. They are just some labels or indices or coordinates of these A and E. A and E are operators. R and R1, R2, they are not indices. If you find this kind of uncomfortable, let's imagine the case where we have a set of localized qubits, right? Say the first, the second, the third, the fourth, the fifth, and so on. Say this is the x-axis. We often talk about the spin operator, for example, for the first one, for the second one, and so on, right? You are totally comfortable with this. But what we are writing here is really the spin operator at position R. This R is not a quantum mechanical operator, it's just a label of the operator we have.
But the spin operator is R cross P, or even later classical analog of spin operator in classical sense.
Spin operator is just the spin operator defined by its matrix elements. It's not necessarily any R cross P.
Yeah, but
In particular, spin is never R cross P. the orbital angular momentum, you can say if I have only one particle is r plus p.
Yeah, but there's no classical analog of spin operator in classical sense. But for the magnetic vector potential, you are deriving from the classical sense. So why can't we say that in the classical sense you have a vector potential, you can Taylor expand it in terms of position, and then you bring it to quantum sense.
That's not how it comes from. This kind of commutator should be viewed as an assumption of the quantum theory.
Okay.
One way to derive it is to, if you call that a derivation, is that we start from the Lagrangian description of the classical theory, and we declare that the same Lagrangian describes the quantum system. But I need to put the Lagrangian into something called path integral. From there, you can also derive this. But you need to assume path integral. I don't plan to talk about path integral in this class. Do you also have a question?
If E is an operator, how did you manage to say that it commutes with AR in the first verification of the
Here?
Yes, like you said that you could pass the nabla of E to the other side.
Yeah, E just commutes with little a. I should have told you this.
Okay.
So the non-trivial commutators are here. Other questions? Go ahead.
Are all fermion charged? Like,
Not all fermions are charged. Neutron is not charged.
so this A is charged particle.
It's a charged particle which it can either be boson or fermion. It can be electron, it can be the bound state of 3 electrons, then it will carry charge 3. It can be a bound state of 1 electron, 1 positron, and 1 electron. The charge would be the same as the electron charge. It cannot be a neutron, which doesn't carry charge. It can also be a boson, for example, the bound state of 2 electrons, then it carries charge 2 in units of electron charge. Other questions? Okay, so this Hamiltonian is invariant under a huge set of transformations, and those transformations are generated by the Gauss law. Then the last slide we want to talk about today is to tell you what is a gauge theory. So it turns out that the theory of electrodynamics is really an example of a so-called gauge theory. And a gauge theory is a theory where the Gauss law is imposed exactly. What this means is, previously I mentioned those are not the correct basis states of quantum electrodynamics, of quantum particles moving in the electromagnetic field. Instead, the correct states in general, that we rather state as physical state as this. This symbol stands for physically valid states. By definition, a gauge theory is a theory where the Gauss law is imposed exactly in this sense. This operator acting on the physically valid state just gives 0. So classically, this thing is equal to 0, and you may interpret the classical result as saying that the expectation value of this thing is equal to 0. No, in the quantum gauge theory, this operator itself as a quantum mechanical operator is just the 0, it's the 0 operator. And the rho 0 is some background charge which you can choose. This part is the same number. Then this brings in a lot of consequences. First, it says that the Hilbert space of a gauge theory is only a subspace of the naive Hilbert space. This is kind of similar to the identical particles. So if we have 2 particles, naively we expect the Hilbert space is the tensor product of 2 Hilbert spaces of the individual particles. But if they're identical, that's not the real Hilbert space. Only the subspace where the states are symmetrical or antisymmetrical will be the right one. Here too, not all these states are valid states. Not all these states are valid states. By definition, only states where the Gauss law is imposed exactly are valid states. This is the definition of a quantum gauge theory. Second, it also tells us that the gauge transformation is a doing nothing transformation because this Gauss law G acts on the physical state is just a 0, so exponential activity is just a 1. This is doing nothing, so this is not a symmetry. Gauge transformation doesn't correspond to any symmetry. If you have heard of something called gauge symmetry, that's really something that should be put into the trash bin of history and be forgotten. It's not a symmetry. Another consequence is that all physically valid operators should be gauge invariant. When I say a physically valid operator, I mean an operator that really acts in the correct Hilbert space. Meaning, if it acts on a state that is physically valid, it returns to me a physically valid state. That is to say, suppose this operator is O, it acts on the physically valid state, the resulting state is O acting on this state, right? This state should be a physically valid state. So by definition, the Gauss law operator acting on it is 0. But on the other hand, this operator can also be written this way. I'm just rewriting it with the commutator. And we know that G acting on this state is equal to 0 by definition. So this commutator acting on 0, acting on any state gives me 0. Acting on any state gives me 0. This means this commutator by itself is the 0 operator. This is just a 0. Because this is 0, on the gauge transformation, this operator will also not change because gauge transformation is just generated by something like this. O times the conjugate. This is just equal to O itself. It's equal to O, it's not equal to 0. And it's equal to O itself because G has a commutator with O being 0. You can easily see this by using the e to the IA times B times e to the IB equation, right? And if we want to look at some examples of physically valid operators, or gauge, these operators are also called gauge invariant operators because they don't change, they're invariant on the gauge transformation. Some examples of gauge invariant operators include E and B and A dag A, and the so-called Wilson-9 operator, which will be discussed next week. From here, you can also see, previously we said, you see those operators are this one and this one, also this one and this one. They are related by gauge transformation. As you see here, for the physically valid states, gauge transformation is not doing anything. That's why those operators related to gauge transformations should all be identified. So this is the structure of quantum gauge theory. It's really more important than any Hamiltonian of the gauge theory. This is the most important part of a quantum gauge theory. Gauge theory is a theory where Gauss law is imposed exactly. Okay, that's what I want to talk about. Any questions?
So what is the basis of the state?
You will see it next week. I will know it on Thursday.
Why is Gauss law so special?
This is more obvious from the Lagrangian formulation of electrodynamics. In the Lagrangian description, you can figure out what is the canonical momentum of something like. You will see, I mentioned the canonical momentum of V is just 0. You will see that in the Lagrangian description, the time derivative of V actually doesn't appear in the Lagrangian at all. Instead, V is multiplied with the Gauss law. This means V in the Lagrangian will just impose the Gauss law exactly. On the other hand, the other parts of the Lagrangian will tell you that E and A, they are canonical conjugates. So in summary, the short answer is that it's so special because it comes from, it can be derived from the Lagrangian description of electrodynamics.
Can you write down the Lagrangian?
The Lagrangian, in simple forms, the Lagrangian looks like this. mu and nu, they run from their t, x, y, z coordinates. And in Japan, summation rule is used. Mu and nu will be summed over. This is the Lagrangian of electromagnetic field. If you also want to have charged particle, then there's one more term.
A0 is V.
A0 is V, yeah. If you want to include charged particle, there's one more term, which is, here distributes the current and is coupled to A. Lagrangian formulation is actually very useful. Yeah, from the Lagrangian formulation, you just apply what you learned in classical mechanics. You will see what is the canonical momentum of what. That's what I want to talk about. If you have any question, you can stay here and ask. Otherwise, feel free to go. Yeah, please.
So what's the Gauss operator actually doing?
What is what?
The Gauss operator G actually doing?
What does it mean?
Yes.
What do you mean? What does it mean?
So does it have a physical meaning like the Hamiltonian operator, like the angular momentum operator? Does it actually give out something? Or does it just like a mathematical definition that some kind of definition is true?
It's the zero operator, as you can see.
So it's the generalized zero operator?
Yes, the zero operator in the physical Hilbert space. So the physical Hilbert space is defined to be the subspace that is made of the eigenstates of this operator with eigenvalue 0.
So can we see zero operator as part of G?
You mean the naive zero operator?
Yes.
In the physical Hilbert space, yes, they are identified. Yeah.
I'm not completely sure, but I think it would be beneficial to ask this question. So the Hamiltonian you showed before in the second condensation form, I think it is very different from the Hamiltonian we've seen in the previous course.
Previous course?
And in this course, yes.
Is it?
Isn't it? I mean, you're writing it in the integral.
Yeah, we also saw it in the previous in week 3.
And yeah, but for example, in the harmonic oscillators, we derive the A and A dagger from the operator of P and X. Here they are occurring in simultaneously. I mean,
Yeah, but we have seen such Hamiltonians from week 3 all the time. And in assignment 3, I think you did the assignment your painful assignment deriving the wave equation based on such Hamiltonian, right? People have seen this all the time. Yeah.
Why do we choose the G according to the Gauss law? Is there other kind of some kind of G like which does not depend on the Gauss law?
You can define other theories, but the gauge theory is defined in such a way.
So gauge theory is only restricted to Gauss law.
Gauge theory is a theory where the Gauss law is imposed exactly.
So imposed exactly means this equation is true.
Yeah,
Okay.
for any physical state.
Which means for every gauge transformation we can find out the related Gauss law.
Yeah. For any gauge theory, you can find the related Gauss law. That's the generator of the gauge transformation. I haven't finished everything I want to talk about. Feel free to go. But if you have questions,